Hello students, let's go to section 2, Rules of Probability 1. Here we are going to cover addition rules and inequality rules. But first, let's have some brief reminder on what we studied from section 1, Axioms of Probability. All three are important, but pay particular attention to the last one here, which we call the addition rule. Okay, the next tool that we need, Venn diagram and logic. A and B versus intersection. A or B versus union. So in short, and makes it smaller or makes it larger. Finally, not A versus a complement. By the way, our textbook author uses A prime for complement, but me, I don't like A prime very much. I don't like to get confused with derivative notation in calculus-based courses, so no, I'm not going to use A prime. Instead, I'm going to use AC, the C notation for complement, which is standard for K-12. Especially if you're taking Texas exam or anything related to education, teacher preparation, anything related to K-12, by the way, then you gotta know the C notation. That's standard for K-12. Okay, next, here's some more Venn diagrams. A or B, but in this case, mutually exclusive, so you have union plus instead. This is set minus, A minus B basically, A but not B. So from A, from this circle, subtract away those in B. So this part is all out, so what's left is this crescent point. Similar thing goes over here. B but not A. B set minus A. Alright, now let's have an example problem. This time let's go to 3 events put together. So here we go. First, A or B or C. Oh, that's easy. Or makes it larger. So include everything here like this. Next, A and B and C. That too is easy and makes it smaller, so it goes inside. Only this part is covered by all three of them. So here. Now, A and B or C versus A and B or C. Wow, this sounds really bad. A and B or C. A and B or C. What's the difference? Well, I exaggerated some changes here when I read, but it's really confusing. You see, what's the difference besides this location of comma? But then again, please remember, it's not mathematics that's making this complicated. Actually, mathematics is making it clear. It's the human language that's making this thing complicated. Math actually helps you. Here in this case, A and B is put together, comma, and separated by this comma. So A and B must be done first. In terms of mathematical logic, you use parentheses to put together like this. A and B first, use parentheses, or C. So let's do A and B first. So brown football shape here. Next, or C, so put together this one too. See, you have this colored region. On the other hand, how about the next one? A and B or C. This time you have to do B or C first. So let us use parentheses to put together. Again, you're witnessing how useful mathematics is. B or C, that first. So here, take this figure 8, entire figure 8 down here. All these where my mouse is running around. And then and A, so we take only the part inside of the circle A. That's this part. The purple part. So the difference between A and B or C versus A and B or C. This time I de-emphasized comma and you couldn't hear any difference at all, right? Alright, let's go to the next example. A and B, but not C. A or B, but not C. What are those? A and B, so we have this part first. Football first, but not C, so take C out, so we go outside here, like this. Next, A or B, so entire figure 8, or maybe snowman, but not C, so we go out over here, like this. Alright, so much for the exercises on Venn diagrams. Now let's go to Rules of Probability 1, Addition Rules and Inequality Rules. We're going to study multiplication rules later. So here are some addition rules. And the very first is nothing more than the axiom itself. A simpler version. So we have two separate sets, two mutually exclusive events. The probability of mutually exclusive union is just sum of the probabilities. By the way, why do we have a proof here? Isn't it the same as the axiom? Well, surprisingly, it may. Yeah, we need proof, but we are going to do that in a separate video. Don't worry. Next, what if we have the usual union, not mutually exclusive union? We have to consider the overlap. How do we do that? One way to decompose completely. A but not B, blue crescent. B but not A, red crescent. And finally, A and B, the purple football. They're all mutually exclusive, so add them all up, and there you go. A or B, or A union B. That's the method I personally prefer. Decompose everything, complete a Venn diagram, and then add up appropriate probabilities based upon shading. Here's another way to handle it. A or B is just all of A, all blue, and B, all B put together and add them together. In that case, this purple part is added twice. So take it off to make it fair, and there you go. This works. And finally, complement. In that case, A and not A add up to 1 because together they cover entire sample space. Okay, so much for addition rules, and then here are inequality rules. So A is part of B, A is subset of B, then probability of B is greater than or equal to probability of A, as you can see in this Venn diagram. Pretty clear, isn't it? But it'll turn out the proof is not that clear. Actually, excuse me, it's clear, but not that easy to understand. We'll do that in a separate video. Now, how about this? If you have a union of a bunch of sets or a bunch of events, then the probability of the union versus some of those probabilities. Well, if they're all mutually exclusive, then we have equality, and that's coming from that axiom of the probability, the third axiom. But in general, we have overlaps here and there, so many are doubly or triply or quadruply covered. So this part is actually bigger, as you can see here. Entire red, entire green, entire blue added up separately, then these middle parts are doubly, sometimes triply counted. So yeah, and we get something bigger in general. And equality holds when they are all mutually disjoint. You can see those, but to prove it in general and to do that for infinitely many, that's going to be a hard work, but we're not going to do that yet. We'll prove all these in a separate video. So much for the theory part, and are you all ready for example problems? Great. We're going to go to an example problems. Those two example problems will be covered in a separate video. Stay tuned.